Okay, we've looked at rotational kinematics and we've looked at torque. And before we get into rotational dynamics, so if you remember, dynamics is forces where things are moving and accelerating, we're going to look at rotational statics. So if you recall, static means not moving or in equilibrium. So what we're going to look at is the rotational equivalent of those situations where forces, or in this case torques, are balanced. So let's start with just defining what something known as the center of mass is. The center of mass is a single point where all of an object's weight is concentrated. And I'm sure you've heard about this before. The center of mass is where an object will balance. So we'll see some demos in class where we are balancing things and they might look weird because the center of mass is located somewhere where it might not be readily apparent. So in other words, for objects such as a sphere, a uniform sphere, the center of mass would be the center of the object. But that's not always the case where the mass isn't concentrated uniformly, if that makes sense. So the center of mass is where the object will balance. You might also see it called the center of gravity. So for our purposes, center of mass and center of gravity are the same thing. An object that is free to rotate about a pivot will come to rest with the center of gravity, or this could also be, as I said, mass. Center of gravity or center of mass below the pivot point. The torque due to gravity when the pivot is at the center of gravity is 0. So all that means is that the sum of the torques equals 0. And again, this could also be mass. Your book uses the word center of gravity, so that's why you're seeing both here. And the center of mass tends to lie closer to heavier objects or particles that make up an object. So in other words, however mass is distributed, wherever more of the mass is distributed is where the center of the mass will be. And we will see this when we do some demos, how this all works out. Okay, so next we want to look at equilibrium, and equilibrium, remember, means balance. So equilibrium, also known as balance, is a state where there is no linear or angular acceleration. So that means that the net force and therefore the net torque are both 0. So before we even look into situations where objects are accelerating and looking at the sum of the torques being a non-zero number, we're just going to look at situations where things are balanced and at rest. So how do we solve equilibrium problems? Similar to how we would solve for our Newton's first and third law problem. So if you remember, before we looked at acceleration with forces, we just looked at objects that were either moving at constant velocity or not moving at all. So with equilibrium, we're going to do the same thing. We're going to draw diagrams and see where the forces are and where they act. It's not going to look as balanced as our force diagrams because you're going to have, say, here's your diagram. So let's say you have a force over here and a force down here. You're going to have different amounts, so it's not going to look as balanced. You're going to choose a pivot point if one's not already given, and then you're going to solve for the torques. So remember, the pivot is the point about which an object would rotate. So a lot of these pivot points are going to be close to where the center of mass is. You're going to set the net torque equal to 0, being careful with signs. So remember, counterclockwise is positive, clockwise is negative, and then you're going to solve for whatever unknown value it's asking for. So a lot of times these problems will ask you either for the pivot point, the distance where a force needs to be applied, or the force itself. All right, so let's do an example. We have 3 objects balancing on a massless board as shown, and the board is balanced. Part A, we want to know what forces act on the board. Part B, how much torque is provided by the 2 kilogram object and the 5 kilogram object. Forgot the question mark here. And part C, how far away from the pivot should the 8 kilogram box be? So we'll start with the easy one. You've got 3 objects. Here's your pivot point right here. So this is the point about which it would rotate. and you've got 3 objects, the 2 kilogram, the 5 kilogram, and the 8 kilogram box. So the forces that are acting on the board, and when we're talking about this, we're talking about forces that would cause torques. You're going to have a downward force from the 2 kilogram object, a downward force from the 5 kilogram object, it will be larger, and then a downward force from the 8 kilogram object. All of these forces causing those rotations would be Fg. So it would be the weight. And then we just want to add, so it's asking what are the forces acting on the board. So it's the weight of each of them. So 9.8 times 2, this would be 19.6 newtons. 9.8 times 5 is 49 newtons. And then 9.8 times 8 is 78.4 newtons. So I'm drawing the diagram, the torque diagram essentially, on the diagram itself. That's fine. So as long as you're showing where the forces are, what direction they're acting, and how far away they are from the pivot, that could count as your diagram. Okay, part B, how much torque is provided by the 2 kilogram and the 5 kilogram objects. Okay, remember, torque is the force times the distance from the pivot times the sine of theta. So all 3 of these forces are at 90-degree angles, so we don't really have to worry about the sine of theta here because that all goes to 1. So for the 2 kilogram object, the torque equals the force, 19.6 newtons, times the distance from the pivot, 2.5 meters. 19.6 times 2.5 is 49 newton meters. This would cause a rotation that way, counterclockwise, so that would be a positive number. The torque from the 5 kilogram object would be 49 newtons times 1.8 meters. 49 times 1.8 is 88.2 newton meters. And again, this is causing a rotation that goes counterclockwise, so this would be positive. So the 2 kilogram object is 49 newton meters, and the 5 kilogram object is 88.2 newton meters. I didn't round here. This would be about 50 newton meters. This would be about 90 newton meters. Okay, the last thing is asking how far away from the pivot should the 8 kilogram box be. So we're solving for x, which is the distance from the object to the pivot. So to solve this, we know that it has to be at rest, which means that your net torque is equal to 0 newton meters. So that means the torque of the 2 kilogram box plus the torque of the 5 kilogram box plus the torque of the 8 kilogram box all have to equal 0. We know what these two values are, so let's just isolate T3. T3 equals negative T1 minus T2. So this equals our unrounded negative 49 newton meters minus 88.2 newton meters. So this equals 137, negative 137.2 newton meters. Torque equals force times the radius. We already figured out what the force was. So torque over force will give me that distance. Negative 137.2 newton meters divided by 78.4 newtons equals, let's see, 1.75 meters away. So x equals 1.75 meters. 1 sig fig, x is about 2 meters away. Okay, I'll do one more example. If you felt okay with this, then you don't have to watch it. But just know that whenever we're solving for an unknown value for problems with equilibriums, you're setting the net torque. So T net, you might also see this symbol, sum of the torques, equal to 0. And then from there, solving. Okay, so let's do one more example if you're still watching. John and Sally are sitting on opposite sides of a seesaw. John is 4.5 meters from the fulcrum, so fulcrum is the pivot. So fulcrum is also known as the pivot. And Sally is 5 meters from the fulcrum. If Sally has a mass of 45 kilograms, what is John's weight if the seesaw is not moving? So here we need to draw a picture. You have a seesaw. Here's the fulcrum. You've got John on one side and Sally on the other. And it says that John is 4.5 meters away and Sally is 5 meters away. This is not drawn to scale. So let's just list a given here. Radius for Sally is 5 meters. Radius for John is 4.5 meters. It tells us that Sally's mass, so mass of Sally, is 45 kilograms. It's in equilibrium, it's balanced, so we're looking for John's weight, Fg, to keep that balance. I'm just going to redraw the diagram. So we have, here's our pivot. We've got the weight of John, and we've got the weight of Sally. And then we have the distance. This is 5 meters, and this is 4.5 meters. Okay, so my total net torque is equal to 0, which means that the force of gravity for Sally times the radius of Sally plus the force of gravity for John times the radius for John equals 0. Okay, so we know that Fg is just mg, so that's easy enough to find for Sally. So Fg for Sally would be her mass, 45 kilograms, times 9.8 newtons per kilogram. So her weight, Fg for Sally, is 441 newtons. Okay, so I'm just going to solve this a little bit differently than I did the last one. The last time I had solved for things separately and then put them in. Here I'm just going to do it algebraically and isolate what we're looking for. So trying to solve for John's weight, we get Sally's weight times her radius divided by John's distance, and that's going to give us John's weight. To move this down. Okay, so this equals 441 newtons times 5 meters divided by 4.5 meters, and that equals the weight of John. So 441 times 5 divided by 4.5 means that John's weight is 490 newtons. So in order to have the seesaw balanced at the distances that they are, his weight would have to be 490 newtons. If they wanted to trick you asking for mass, divide that by 9.8, his mass would be about 50 kilograms. Okay, so fairly straightforward. There's not a lot of tricks in this problem, or these types of problems. Anything that would be tricky would be giving you forces that are at angles. But again, as long as we know that torque equals Fr sine theta, then it's really not that bad. Just making sure that your theta is between the radius and the force being applied.